Unified dynamics.
Unified dynamics is an active framework reinterpreting standard physics. This presentation is a conceptual overview, not the complete proof. For all formal mathematics, visit udphysics.com. Alright, so this deck is a high-level walkthrough of unified dynamics, or UD, and the main idea is pretty simple at the top level. Spacetime is not assumed as the starting point. Instead, we start with a discrete pre-geometric substrate, and then we test whether smooth spacetime, gravity-like behavior, matter structure, and vacuum normalization can emerge from that substrate. The image here is showing that transition visually. On one side, we have a discrete mesh-like structure, and on the other side, we have a smoother toroidal coframe geometry. So the big theme is, can a rough, finite discrete system relax into something that looks like continuous spacetime? This slide frames the problem. The legacy failure being called out is that standard quantum field theory has trouble when infinite vacuum modes are summed without a clean structural cutoff. UD's answer is to not start with an infinite continuous background. Instead, it starts with a discrete simplicial substrate, specifically a K4 tetrahedral primitive. The simulation result shown here says that a large production run completed, and the important claim is not just that it ran, but that the falsifier tests survived. So the flow is, from the discrete substrate, UD tries to derive three major things: spacetime, gauge structure, and matter, rather than assuming all of them up front. This slide is a comparison table. The left side lists three pressure points: the cosmological constant, scalar fields, and vacuum drag. For the cosmological constant, the legacy issue is the vacuum energy catastrophe. Basically, the naive estimate is wildly too large. UD's proposed answer is screened residue at a transition boundary. For scalar fields, the concern is that they can behave like volatile free fields. UD's proposed answer is that repeated IFS screening pins that scalar behavior down. And for vacuum drag, the issue is that matter moving through a raw vacuum background should experience catastrophic drag. UD proposes a scale cascade shield that protects macroscopic matter from microscopic vacuum behavior. So the claim here is, UD is trying to solve boundary failures structurally, not by adding free knobs afterward. This is the main cosmological constant slide. Rather than reading the equation piece by piece, the meaning is this: the observed vacuum residue is being modeled as a very small leftover after repeated internal screening. The equation says that the cosmological constant is not inserted by hand. It is calculated from a vacuum energy seed, an IFS suppression factor applied 7 times, and a normalization structure tied to the Planck scale. The slide labels this as the n equals 7 topological boundary. In plain language, that means UD is treating the cosmological constant as a finite residue left behind after 7 layers of discrete screening. The key presentation point is, this is a candidate derivation lane. It is not just curve fitting, but we still want to keep the language governed. We can say it is a zero-free parameter comparison result inside the UD model, while physical promotion remains subject to external validation. This slide explains how local scalar noise gets suppressed. The curve starts high at the Planck scale ultraviolet core, where the scalar field is volatile. Then, as the system goes through repeated contraction or decimation, the scalar contribution drops very rapidly. The slide calls out around 230 to 240 levels of decimation. The meaning is, it takes a large number of recursive scale reductions before the model becomes smooth enough to behave like macroscopic spacetime. The bottom statement says the ppn gamma parameter approaches 1. In ordinary terms, that means the model is trying to land on the same weak field gravitational behavior that general relativity predicts. So I would say, this is the GR-compatible Winnet lane, where scalar deviations become too small to matter at solar system scales. This slide is about why macroscopic matter does not get destroyed by microscopic vacuum drag. At the microscopic scale, the model says an unshielded object loses velocity almost immediately. At the intermediate electroleak scale, the shielding is partial, so some core structure remains. And at the macroscopic or cosmological scale, the shielding becomes strong enough that motion remains stable. The idea is that matter is protected by a scale cascade, so the same substrate can be active and volatile at tiny scales, but effectively smooth and stable at large scales. In normal language, the vacuum does not behave the same way at every scale. UD is proposing that recursive shielding is what lets ordinary matter persist. Now we introduce the thermodynamic engine. The basic picture is that localized metric stress builds up, triggers topological reconfiguration, and then cools back down through a Lindblad-style relaxation process. The orange lane is the expansion trigger. It says that when stress crosses a threshold, the system performs a bistellar flip, basically a topology-preserving move that redistributes the local geometry. The blue lane is the cooling trigger. When the system cools through the Lindblad bath, it collapses back into a lower stress configuration. So the simple story is, is, UD does not treat spacetime as fixed. It treats geometry as a dynamic system that can flip, relax, cool, and stabilize. Moving on to the toroidal coframe attractor. The claim is that the 18 discrete transport directions of the S3 shell fold into a toroidal state space geometry. The torus is being used as a stable organizational geometry for the coframe. The outer equator is highlighted because it has positive Gaussian curvature, and the slide treats that region as a global attractor. In plain English, chaotic or mass-like structures tend to organize around the stable equatorial geometry. So this is a visual way of saying the discrete transport shell does not stay random. It relaxes into a smooth organizing shape. Now, into wave packet refraction. Instead of saying gravity is a force in the usual way, UD is modeling gravity-like behavior as wavefront refraction. Packets follow paths where the phase delay is minimized, similar to Fermat's principle in optics. The charts show different kinds of scaling: temporal, spatial, and cusp scaling. The side panel shows caustic intensity mappings at different meridian positions. The big takeaway is, phase space density collapses toward the outer equator, and the geometry naturally creates lensing-like behavior without inserting a separate gravitational lensing rule by hand. This slide is about defects. The torus image shows localized curvature hotspots, or vortex cores, moving across the coframe geometry. The heat map shows where strain energy is concentrating and dissipating. The timeline at the bottom has 3 parts. First, before annihilation, active vortex cores create localized curvature. Then, during the annihilation flash, opposite charges pair off and collapse, releasing strain energy. Finally, after the event, the system recovers into a smoother, torsion-suppressed state. So the simple version is, defects form, migrate, collide, release energy, and then the geometry relaxes. Comparing packet trajectories to null geodesics. The phrase null geodesic just means the path followed by light or a massless wave packet in curved spacetime. The plot shows packet paths bending around a central structure. The right side telemetry ledger says that at larger impact distances, the packet shows clean hyperbolic deflection, which is the standard kind of bending we expect from gravity. Near the horizon region, the model says the packet still behaves gracefully because the ultraviolet core is regularized, meaning the model avoids an infinite crash at the center. The key claim is that gravity is being recovered as refraction of a traveling wavefront. This slide is a stronger comparison to Schwarzschild geometry. The plots show metric components relaxing toward the expected Schwarzschild-like behavior. In plain terms, the model is testing whether the emergent substrate produces the same radial and time behavior that standard black hole geometry predicts. The left note says the time-like component aligns with Schwarzschild outside the event horizon. The right note says the space-like component regularizes smoothly through the horizon. So the presentation point is, UD is claiming that the discrete substrate converges toward a familiar GR geometry, while potentially avoiding classical singularity behavior through smooth internal regularization. And finally, the verdict slide. It lists 4 gate categories: accretion and refraction, geodesic conservation, topological decay, and equatorial attraction. Each gate is marked as passed in this internal diagnostic lane. The bottom line says the 13-layer stack is sealed, and that the discrete capacity-limited substrate mathematically guarantees continuous general relativity. Within this diagnostic stack, the substrate has passed the internal gates required for a GR-compatible continuum limit. That keeps the claim strong, but still responsible. So the closing message is, UD is not starting with spacetime and quantizing it. It is starting with a finite discrete substrate and testing whether spacetime, gravitational refraction, scalar suppression, and vacuum normalization emerge from the same governed structure.
Don't forget to like, subscribe, and share, and keep questioning reality.